Here we go, the side splitter theorem. Some of its uses and proof. So the proof will be at the end, so if you don't really care about the proof, all you want to do is know how to use this thing, then just watch the first about 4 examples, which will take me about 5-6 minutes to get through. The rest of the 6 minutes on the video, or 8, will be for the proof. So what the side splitter theorem is a line parallel to a side of a triangle intersects the other two sides so that the resulting segments are proportional. So here's just a basic problem on how to use it. So we want to find AD over here, that length. These lines, DE, is parallel to the base here, AC. And the theorem states that BE, EC, DB, and AD will be proportional. In other words, 10 over 7 will be the same as 18 over AD. And in terms of solving this, you can cross multiply, can do lots of different things. I always like to get common denominators so I don't get this and multiplying mixed up, which happens a lot with people. They end up cross multiplying by everything. So you'd multiply the left side by AD to get a common denominator, multiply the right side by 7 to get a common denominator, and then multiply by the whole thing by AD and 7. And what happens is the 7's cross out, the AD crosses out, and you're distributing it through both sides, and so these would also cross out. So we know that 10 AD equals 18 times 7, which is 126. And then you divide by 10. On the next one I'll just do cross multiplication, but that's really what's happening there. We're using, these are rational equations, and we're finding the common denominator so we can solve the equations. So AD is 12.6. There you go. That's how you use the side splitter theorem. So let's try it on another one. Go ahead, hit pause on the video, give it a shot on this one, and then watch me solve it. So in this case, we're looking for AD again. And so here we have 9 over AD equals 4 over 12. And so 9 over AD equals 4 over 12. If you cross multiply, that would be 4 times AD equals 9 times 12. And then 9 times 12 is 108 equals 4 AD. Then to get rid of the 4, you divide both sides by 4, and you would find out that AD is in fact 27. What's always good is to go back and look. These are done proportionally, so does this look like 27? Well, to me it does, because this is 9, and so it looks about 3 times the size of that 9 there. So the answer makes sense. Okay, it also extends to if you have 3 parallel lines. If you have 3 parallel lines, you do the same thing. You can go through and go n over 12 equals 4 over 10, and cross multiply. So 10n equals 48. Then you divide both sides by 10, and n equals 4.8. Now what's kind of nice about this is you don't necessarily have to go in that order. You could also go in, as long as you don't crisscross. In other words, you could set up the proportion n over 4 equals 12 over 10 and end up with the same thing. Same with back here. You could have also set up the proportion as 9 over 4 equals AD over 12, And a lot of that can be proven with the properties of proportions. But you always want to be careful. So let's say we're looking for AC in this case. Okay, AC in this case, if you use that same side splitter for, say, DE and AC, we'll have a problem, and I'll show you what happens here. So if you set it up the same, and this is wrong, but it happens a lot. This happens with a lot of students. So we know 3AC equals 18 if you cross multiply, and then you divide by 3, and AC equals 6. Well, if you look at that, AC being 6 doesn't make any sense at all in this image. It should be bigger than DE. So we've got a problem, a real serious one. So this doesn't work. So what we're going to have to do instead is split the triangles up into similar triangles. So we know this angle, they share that angle, this small triangle, which I'll try and draw it as best I can. So that's 8, that's 3, and that's 9. And then the big triangle, well, that's kind of pathetic attempt. That's better. Not much bigger, but that'll work. Wow, that's pretty horrible too. But this one would be 5, because you'd add up the 3 and the 2. This would be X. We don't know it. That's the AC. Got a little glitch there in my board. So let's give it a shot. So if we use proportions of triangles, I'm going to go small to big. Your scalar factor would be 3/5 is the same as 9 over X. And then you can solve that. So that would be 3X equals 45 if you cross multiply, and X equals 45 divided by 3, which is 15. And so there's the actual answer, which makes a lot more sense. If that looks like even looks like 15. So if you're done, if you're just after the uses of the side splitter theorem, then you're done with the video. But if you're curious as to know, well, how do we know it works? How do we know it's true all the time? That's the next part. And so I'm going to go through the proof with you here. Now this proof that I'm going to go over with you is not going to be an efficient proof by any means. It's just going to be kind of basic and not necessarily a beautiful proof either. Some mathematicians will probably go crazy when I do it. So I'm going to shrink that up so we can come see it in a second. But we're going to start out with the given, which is the fact that DE is parallel to AC. And then because of that, we're going to prove the two triangles are congruent, or not congruent, but similar, the small one and the big one, like I drew out previously. And so we know for a second step, since the triangles are, or since those lines are parallel, we know that angle BAC is equal to angle BDE. So I'll mark that on my triangles. So here and here, those two angles are equal, and those, the reason for that is corresponding angles. So I'm going to call it CORR, angles of parallel lines are congruent. Okay, we also know that both triangles, the small one and the big one, share angle B. So we know that angle B is congruent to angle B. And that's called the reflexive property. So there we go. So once you know that two angles are congruent in the triangles, we know that triangle BDE is congruent, or not congruent, is similar. Is similar to triangle BAC. So hopefully you're also getting kind of familiar with some of the symbols for similar, congruence, things like that. And that's the angle similarity theorem. And so there we have it. So we know that this triangle here is similar to the big one. I'll put it in red. Okay, there we go. Once you know that, we can use some information to start setting up some proportions. We also know that these two, that segment is the combination of BD and AC, or sorry, BD and AD. So that's the next thing I'm going to do here. And we're also going to use the similarity to set up a proportion. Since we know those triangles, maybe we should do that first. Like I said, I'm not a perfect proof guy, but we know because the triangles are similar that BD over BA is equal to BE over BC. I guess you don't need that little line segment there because we're dealing with lengths here. And corresponding sides of similar triangles are proportional, would go here. So corresponding sides of similar triangles are proportional. Okay, now we can do the angle addition part of the proof. So we know that BA, I better hurry along here, equals BD plus DA, and we also know that BC is equal to BE plus EC. So that is strictly from the angle addition postulate. Okay, so just the angle addition postulate. Whoop, and that's, I don't know why, oh I see, it's supposed to be an EC and it just didn't register the little mark I made. So BE plus EC equals BC. Alright, once we have that, we can do some substitution. So now we know that we have BD over, and instead of BA, we know BA is equal to BD plus DA. And so we also know then that BE, instead of BC, we know that BE plus EC could go there. And that's by substitution. Okay, sorry I'm a little sloppy. Trying to hustle along and it always makes me kind of sloppy. Then we know we can go ahead and get common denominators or cross multiply. There's other properties that it's called, but we're just going to jump right into, I like to do the identity property. So I'm not going to put this in the proof, but basically I'm going to take both sides by 1, which is the multiplicative identity property. And I'm going to use a kind of a useful one instead of just 1. I'm going to use the common denominator on both sides, which would be on the left side I need a we're missing a BE plus EC over BE plus EC, and then times BD over BD plus DA, and the same over here, BE over BE plus EC, and the same times 1 times the other side, which is BD plus DA over BD plus DA on top and bottom. Again, you could also be cross multiplying that, and so that's substitution property. And then what happens is you could multiply by this common denominator and those would eliminate. Again, I'm trying to hustle along here. So BD times BE plus EC is equal to BE times BD plus DA. So I multiplied by, that's the multiplication of equality to eliminate those. They'll cross out. That would go here, multiplication of equality. Then we distribute, so we know BD times BE plus BD times EC is equal to BE times BD plus BE times DA. And those end up, that's just distribution, distribution. And then notice we have a BD, BE. Yes, those two are the same on both sides. So you could subtract that out. So there's your next line. And we know that BD times EC equals BE times DA. And that's from subtraction. I could subtract those out. And we're just about done with the proof. So at this point, we're going to multiply, or we're going to divide both sides by, because you look at what we needed to find, and I need to kind of hustle here, but we needed to have a BD on top and AD on the bottom, or right here. Excuse me. A BE on top and EC on the bottom. And so we're going to divide both sides by each other. I'm going to combine it into one step. So divided by DAEC, and we're going to take that top here, BEDA, divided by the same thing, DA, that's multiplication of equality again, EC, so mult equality. And notice what happens. The ECs can't divide out, so we've got fancy ones there. DAs simplify, and so we know that BD now over DA is equal to BE over EC. And the reason for that, again, these are ones. Both of those are ones. So you could maybe put useful form of one, or again, I would put multiplicative identity, because again, it is just one. So there's the proof. We've proven the side splitter theorem. So that's 20 minutes. That's a long time, but it goes through everything and you don't have to watch it all. So hope it was helpful. Be curious if anybody made it clear to 18 minutes on this video, but I doubt it. Have a good one.